This is section 4.1. Section 4.1 is about eigenvectors and eigenvalues. Typically, this is a section that is extremely important because you're going to see this in a lot of future classes. Not only math classes like differential equations, but engineering classes if you take some of those as well. So pay close attention to eigenvectors and eigenvalues. Section 4.1. Right, first we get the definition of what an eigenvector and an eigenvalue is to start with. Let A be some square matrix, an n by n matrix. Let U be a non-zero, very important you see that non-zero right there, n by 1 vector. And lambda is just a constant. Okay, we just as easily could have called that Q or something. It's just traditionally been called lambda, so don't let the Greek letter there throw you off. People find it confusing just because it's strange looking. Okay, if it makes you happy to put an L there, put an L there. So A is a matrix, U is a vector, lambda is a constant. If A times U is equal to lambda times U, now notice what that says. We have a whole matrix, A, which is an n by n matrix. We're going to multiply that n by n matrix times an n by 1 vector, U. Okay, now remember, with the sizes corresponding like that, I'm going to get an n by 1 vector as my answer. So A times U is a vector. Lambda times U, because lambda is a constant, is also going to be a vector. And what we're seeing is that we're going to get the same result if we multiply the whole matrix times U as if we just multiplied a little old constant times U. You can see how this is going to be a pretty important situation. If this is true, then lambda is called an eigenvalue for the matrix A, and U is called the eigenvector corresponding to lambda. Okay, so we'll typically start with the matrix A, then we'll find eigenvalues, then we'll find eigenvectors corresponding to lambda. Now we sometimes have to go out of order because maybe they give us A and maybe they give us U and we have to find lambda, but usually the problems will give us A, we find lambda, and then we find the eigenvector corresponding. We find the U. Okay, so lambda's eigenvalue, U would be called an eigenvector as long as that AU minus lambda U, equal to lambda U is true. All right, for example, here's one of the ones that they give us A, they give us U, they want us now to find lambda. Okay, so A is 3, 5, 1, negative 1 in a 2 by 2 matrix, and U is negative 10, negative 2, the vector. We want to find lambda that corresponds to the eigenvector U. Okay, well, if you remember, if it is an eigenvalue and if U is an eigenvector, then AU is going to be equal to lambda U. So all I need to do is take the original matrix A, multiply it by U, and that's going to give me the same thing that lambda times the vector U would give me. Okay, so on the left-hand side, if we work that out, the first row, 3, 5, times the column, negative 10, negative 2, I get negative 40. And then the second row, the 1, negative 1, times the negative 10, negative 2, I get negative 8. So I have negative 48, that vector, is equal to lambda times negative 10, negative 2. Okay, just working across the top. Negative 40 is equal to lambda times negative 10, so lambda has to be 4. Now double check with the second entry, because it's possible that they've given us one that doesn't work. So let's make sure that negative 8 is equal to 4 times negative 2. Well, it is. So everything's fine. Lambda's 4, and we've solved for lambda. Okay, so do be careful that all of the entries do match up and that you get the same lambda every time with each row. Okay, there's a theorem next that says lambda is an eigenvalue for A if and only if, And remember, if and only if means one implies the other and the other implies the first. So I'll go over this in just a second a little bit more thoroughly. But it's kind of that double arrow, one implies the other. Okay. If and only if A minus lambda I is not invertible. Okay, A minus lambda I, that's the matrix A minus the constant times the identity matrix that corresponds. You want to use the same size identity matrix as A. So A minus lambda I is just a matrix. And what we're saying is that lambda is an eigenvalue if that matrix is not invertible. Recall, a matrix is not invertible if and only if, there it is again, its determinant is 0. So the determinant of A minus lambda I is going to be equal to 0 when lambda is an eigenvalue. And here's the if and only if part. One implies the other. And lambda is an eigenvalue when the determinant of A minus lambda I is equal to 0. Okay, so what it's sounding like is that if we want to find lambda, we're going to use the fact that the determinant of A minus lambda I is equal to 0. That's going to give us lambda. Okay, for example, let's say that A is 5, negative 1, 2, 2, and it says to find the eigenvalues lambda. So I might get more than one value for lambda. Okay, well, using the previous information there, we're going to set the determinant of A minus lambda I equal to 0. That was on the previous screen. Set the determinant of A minus lambda I equal to 0. Okay, so first I probably ought to work out what A minus lambda I is. Okay, if I do that, A minus lambda I, now lambda is just a constant, but I have to leave the symbol there. A was 5, negative 1, 2, 2. Minus lambda times, I want to use a 2 by 2 I matrix. So the 1, 0, 0, 1 is the I matrix right there. That's equal to 5 minus lambda in the first position, negative 1 in the first row, second column. In the second row, first column, I get a 2. And then in the second row, second column, I get 2 minus lambda. And you can kind of make the generalization that what's going to happen each time is that the main diagonal is going to have a minus lambda attached to each of the entries. Every other entry in the original A matrix is going to be unchanged. Okay, so I have the 5 minus lambda, negative 1, 2, 2 minus lambda. And what I'm going to try to do is set that determinant equal to 0. Okay, the determinant of that, if you remember how to do a determinant of a 2 by 2, it's going to be 5 minus lambda times the quantity 2 minus lambda, and then minus negative 2, which winds up being plus 2. Okay, now working out the first part there, I get 10 minus 5 lambda minus 2 lambda plus lambda squared plus 2 is equal to 0. Okay, my goal again was to solve for lambda. So I want to put that into a form where I can easily factor it. I'm used to seeing the lambda squared first, so that's what I chose to do, was just to move it in front. That gave me lambda squared minus 7 lambda plus 12. That's equal to 0. So lambda minus 3 and lambda minus 4 is what that factors into. That means lambda has to be 3 and 4. Okay, so I got 2 eigenvalue values in this problem. It's interesting that I started with a 2 by 2 and I got 2 values. Wonder what that means. Okay, in that example, lambda squared minus 7 lambda plus 12 is equal to 0. Remember that step? That's called the characteristic equation. The characteristic equation. P of lambda, which is equal to that polynomial. In fact, it's sometimes called polynomial, characteristic polynomial. That is a function of lambda. you often see like f of x or whatever. That means there are x's in the problem. P of lambda means that there are lambdas in the polynomial. Now the reason I've shown you the characteristic equation and the characteristic polynomial is because often problems will ask you not just for lambda values, but for the characteristic polynomial. So instead of asking for, lambda, which was 3 and 4 in the previous example, they might have asked you, hey, find the characteristic polynomial, or maybe asked you for both, maybe asked you for lambda and asked you for the characteristic polynomial. Okay, let's now look at a 3 by 3. Say that A is equal to 4, 0, negative 2 in the first row, 5, 3, 0 in the second, 6, 0, negative 4 in the third. Now find the eigenvalues. Okay, now remember what we did in the past? For the 2 by 2, we did the determinant of A minus lambda I. We're going to do the same thing here. It's just the determinant of a 3 by 3 is slightly more complicated. All right, first find A minus lambda I. As you can see, I put the original A, then minus the letter lambda, times the identity matrix. This time I'm using I sub 3 because I want to use the same size as A. So I have 1, 0, 0, 0, 1, 0, 0, 0, 1 as my I matrix. Okay, working that out. Again, look at that main diagonal. That's the only thing that's changed. I have 4 minus lambda in the main diagonal, then 3 minus lambda in the main diagonal, then negative 4 minus lambda in the main diagonal. All of the other entries are exactly like they were with A. So like I said, you can make the generalization that the only thing that's going to occur when you do A minus lambda I is the main diagonal gets a minus lambda attached to everybody. Okay, now I want to set this determinant equal to 0. The determinant of A minus lambda I would just be the determinant of that matrix we found. And remember that the symbols that look like absolute value parentheses are going to mean take the determinant of for a matrix. All right, now for this 3 by 3, I decided to go down the second column. I went down the second column because there's a couple zeros there. If you make the mistake of choosing something else, now typically you'll get the same answer, right? But it makes it a lot more difficult to do this problem because of the algebra involved. So definitely, if you're really attached to going along the first row or something like that, you need to break yourself from that and go along whatever has the most zeros. Because when you get to these 3 by 3 matrices which lead to third degree polynomials, they're really difficult to factor unless you go at it this way. Okay, so I got 3 minus lambda times, then I just worked out the cofactor, negative 1 to the 1 plus 1. That should actually be 2 plus 2. Whoops, typo. Sorry about that. Negative 1 to the 2 plus 2 times the matrix 4 minus lambda, negative 2, 6, negative 4 minus lambda. Okay, that's going to give me 3 minus lambda times, okay, now work out the 2 by 2 determinant. So I get 4 minus lambda times negative 4 minus lambda, then minus negative 12, which is plus 12. Okay, now working inside of the square brackets, I get negative 16 minus 4 lambda plus 4 lambda plus lambda squared plus 12. As you can see, there's some algebra there. All right, that gave me 3 minus lambda times lambda squared minus 4. Now it's easy when you're doing this algebra to get caught up in doing algebra and then you're like, okay, I need to distribute this all through. But remember what the goal is. Don't lose sight of the goal. The goal is to solve for lambda. The question said find lambda, find the eigenvalues. Okay, so I want to factor this. Okay, our goal is to factor that so you can solve for lambda. Okay, with that in mind, I want to factor lambda squared minus 4 into lambda minus 2, lambda plus 2. Once I do that, remember this was set equal to 0. I get the lambda values of 3, 2, and negative 2. Okay, so I got 3 lambda values for that 3 by 3 matrix. All right, now, if the problem had asked us for the characteristic polynomial, then we would have had to work out the 3 minus lambda times lambda squared minus 4. But it didn't. It asked us for lambda. So we wanted to solve for lambda, so we had to factor the lambda squared minus 4. Okay, so keep in mind what your goal is. If your goal is to find characteristic polynomial, yes, work that out. If it's to find lambda, though, make sure you don't multiply that out, because you'll get yourself in trouble. All right, next theorem. You noticed when we did a 2 by 2, we got 2 values. When we did a 3 by 3, we got 3 values. This theorem says the maximum number of eigenvalues that I can have in an n by n matrix is n. Notice it says maximum. I could get less eigenvalues because if you remember, like when you factor things like perfect squares and so on, you get repeated solutions. So, for example, if I had something like lambda squared plus 4 lambda plus 4, I'd get lambda is negative 2 and lambda is negative 2. I'd get the same thing twice. So that's where this maximum thing comes from. I might get certain values repeated. And in that case, you know, that you wouldn't count them twice. You would just say, oh, well, I've just got a couple instead of maybe 3. Okay, so keep in mind the word maximum. The most that I will get is n. All right, to find an eigenvector. To find an eigenvector, you want to solve the matrix equation A minus lambda I times x is equal to 0. Now, I'm not really going into why you want to do that, but rather how you're going to do that. You're going to do that by reducing A minus lambda I on the left and then 0 on the right. So you're just going to make yourself an augmented matrix, just like we did the very first section, and then reduce it, do the old row operations and get it into reduced echelon form. Okay, so A minus lambda I on the left, and 0 on the right. All right, for example, let's say that they give us lambda is 3. This is actually one of our previous examples, and the A matrix is 5, negative 1, 2, 2. And we want to find eigenvectors that correspond to that. Okay, remember what it said. I want to reduce A minus lambda I on the left, zeros on the right. Well, A minus lambda I, the 5, negative 1, 2, 2, minus, now this time I have a value for lambda, it's 3, times the I matrix. Okay, then work that out. I'm getting 2, negative 1, 2, negative 1. And that's usually what's going to happen when you do a 2 by 2. You'll get the same thing over again in the second row. All right, now next I wanted to reduce this with zeros on the right. So you put 2, negative 1, 2, negative 1 on the left, zeros on the right. Just like it's an augmented matrix, go through your steps. I'm not going to show you all the different steps. Obviously, this is a pretty quick one. But the steps that you'd want to do is like row 2 minus row 1. That's going to give you a 0 in the bottom row. It's actually going to give you zeros all the way across the bottom row. And then half of the top row is going to make it a 1 in the first position. And I wind up with the solution being x1 is equal to half of x2. Because across the top row you'd have 1, negative 1/2, 0, which means 1x1 minus 1/2 of x2 is equal to 0. So in other words, x1 is half of x2. So the x1 value being half of the x2 value, we want to, as crazy as this sounds, pick something pretty for x2. Okay, you want to pick something that you can take half of. If x2 is 2, and I take half of that, then x1 is 1. Now, obviously, I could pick any value for x2. It's an independent variable. There are an infinite number of possibilities for x2. And depending upon what I pick for x2, I'll get a different value for x1. So there's an infinite number of eigenvectors. All I want to do is write the one that looks the nicest. And in this case, the 1, 2 looks really nice. And I got that by choosing a 2 for x2, and that gave me a 1 for x1. So we could have chosen any value for x2. Our eigenvectors are any multiple of that 1, 2. Okay, so I just as easily could have chosen a 4 for x2 and gotten a 2 for x1. I'm just writing down the 1, 2 because it's probably the nicest looking of all of my possibilities. All right, there's a theorem that says for each eigenvalue lambda, there are infinitely many eigenvectors. In fact, they're all multiples of each other. As we saw in the last example, I just happened to write down the 1, 2 and say, well, it's any multiple of that because it looked the nicest. But there's any, I could have chosen any value for x2. So there were an infinite number of eigenvectors. That's always going to be true. Now remember, too, from the definition, the eigenvectors cannot be zero vectors. So I can't have the zero vector in there. All right, in general, we'll get different eigenvectors for different eigenvalues. Had we used lambda is equal to 4 in the previous example, we would have gotten that x1 was equal to x2, so we would have gotten anything like 1, 1, 2, 2, 5, 5, negative 17, any multiple of 1, 1. Now again, the reason I write down 1, 1 is because it looks the nicest. It's easiest to see the multiples of that eigenvector. Okay, but there are an infinite number of eigenvectors for any eigenvalue. All right, that was section 4.1, eigenvectors and eigenvalues. As you saw, there are an infinite number of eigenvectors for each eigenvalue. The maximum number of eigenvalues that a particular matrix has is n, where the matrix is an n by n. Now that's the maximum, so keep in mind you could have less. And also keep in mind that the zero vector cannot be an eigenvector by definition, because remember that eigenvector is always going to be non-zero vectors only. Okay, do a lot of practice with this section. It's a very important section. A lot of questions come from this section on the final exam, of course, and like I said, you'll see it a lot in future classes. So good luck with this one.